All right, let's jump right in. Welcome to today's explainer. We're about to embark on a really fascinating journey to uncover the invisible forces that safely power literally every single aspect of our modern lives. Seriously, have you ever stopped to think about the sheer amount of invisible magic happening around you just so you can watch a screen or turn on a light? It's mind-blowing. So today, we are going to make that magic visible. Let's get started.
Think about this for a second. How is massive electricity actually safe for your smartphone? It's kind of a central mystery of our daily routines. When you plug your delicate, incredibly complex phone into a wall, it connects to a grid powered by a roaring, massive power plant. So why doesn't that immense wave of raw energy just immediately fry your fragile phone battery into a crisp?
Section 1. The Everyday Electricity Mystery. To really understand this, we have to look at the massive mismatch in the scale of power going on around us. On one side, you have the power plant. The national grid generates raw power at this incredibly intense, massive voltage just so it can travel across vast distances to reach your city. But on the other side, we have your phone charger, which only needs a tiny, very precise sip of electricity. This raw power from the grid is way too intense for our homes. It desperately needs a translator to step in and calm things down before it ever reaches our gadgets.
Enter the hero of our story, the transformer. And no, not the robots in disguise from the movies, but an electrical device that acts as the ultimate mediator. It uses something called electromagnetic induction to raise or lower electrical voltage. Basically, it takes that roaring waterfall of power from the plant and gently steps it down to a safe, highly usable stream for your devices.
Section 2. How a transformer works. Now that we know what our hero does, let's dive into the actual magic of how it pulls it off. And the most incredible part? It does all of this heavy lifting without a single moving part. This genius piece of technology is essentially made of just 3 deceivingly simple components. You've got a primary coil where the electricity comes in, a secondary coil where the altered electricity goes out, and a soft iron core that connects the two. That's literally it. But what happens between these components is pure physics brilliance.
Here is how the journey begins. First, the current flows into the primary coil. Because of the specific type of current it creates a shifting, varying magnetic field. This invisible magnetic field is then channeled right through that soft iron core over to the secondary coil. And get this, just by the magnetic field fluctuating around that second wire, it actually creates or induces a brand new electrical current in the secondary coil. The electricity never directly touches from one coil to the other. It's entirely transferred across an invisible magnetic bridge. How cool is that?
What's really fascinating is how tweaking this basic setup gives us 2 distinctly different, incredibly useful tools. If you put more wire loops on the output side, boom, you get a step-up transformer that raises the voltage, which is perfect for pushing power out of a giant power plant. But if you put fewer loops on the output side, you get a step-down transformer, which lowers the voltage. That makes the humble step-down transformer the everyday hero hiding right inside your phone chargers and laptop adapters.
Section 3. Why do we need AC current?
But wait, there is a crucial plot twist to this whole story. Our hero, the transformer, cannot work alone. In fact, without its specific partner, the transformer is completely useless. You see, a transformer can only work with alternating current, or AC. If you try to feed it direct, flat electrical current, absolutely nothing will happen across that magnetic bridge. Nothing. This is the absolute golden rule of electrical distribution. But why?
Well, it all comes down to how AC behaves. Alternating current is an electrical current whose direction and value are constantly changing, pulsing back and forth periodically. If you map it out, it forms a rolling sinusoidal wave. Because the electricity is constantly shifting, the magnetic field it creates in our transformer's primary coil is also constantly shifting. And as we learned earlier, a changing magnetic field is the exact secret ingredient needed to induce electricity in the secondary coil.
Just to give you an idea of how fast this is happening, in Indonesia, for example, the national grid's AC current changes direction 50 times every single second. That's a frequency of 50 hertz. 50 times a second, that magnetic wave is pulsing through the iron core inside your wall adapters.
Section 4. The Secret Calculations of Transformers.
We're going to smoothly transition into the mathematics behind this. But don't worry, I don't want you to look at these formulas as homework. Think of them more as the secret codes that engineers use to design these life-saving devices. There is a brilliant balancing act happening inside the transformer. The first formula shows us that the ratio of the voltage perfectly matches the ratio of the coils.
If the secondary coil has fewer loops than the primary coil, the secondary voltage will be proportionally lower. The second formula shows the trade-off. In an ideal transformer, the power going in equals the power coming out.
Let's ground this math in a really concrete example from our sources. Imagine your primary input coil has 200 loops of wire, and it's receiving 220 volts from the wall. If you build the secondary output coil with exactly 100 loops, which is half the amount, what happens? The voltage is cut exactly in half, right down to 110 volts. Half the coils, half the voltage. It is so elegantly simple and beautifully predictable.
And what makes this technology truly spectacular is its efficiency. When engineers calculate how much power is lost during this magnetic jump, they find that an ideal transformer wastes almost zero energy. They approach 100% efficiency, meaning nearly all the power put into the primary coil is successfully translated over to the secondary coil.
Section 5. AC current versus DC current.
We've talked a lot about AC, but to really appreciate it, we need to bring in its famous rival, direct current, or DC. You might know this as the legendary historical battle between Nikola Tesla's AC and Thomas Edison's DC. And looking at this, we can clearly map out why AC dominates our world's infrastructure. AC changes direction and has a frequency, which means it can be manipulated by our hero, the transformer. DC remains completely flat and constant, making it strictly reserved for localized things like the batteries in your TV remote. Because DC can't be easily run through a transformer, pushing it across long distances without losing massive amounts of power is just incredibly difficult.
And that brings us to the ultimate genius behind our modern power infrastructure. National grids use AC, because alternating current and transformers are a perfect team. The grid uses a step-up transformer to push AC power at massive, highly efficient voltages across miles and miles of wire, and then uses step-down transformers outside your neighborhood and tiny ones inside your device chargers to make it completely safe for your living room. I want to leave you with a provocative thought. What would happen to our daily gadgets, to our entire modern way of life, if the seemingly simple principle of electromagnetic induction was never discovered? We wouldn't have this elegant, invisible bridge translating raw power into the precise energy our lives demand. So the next time you effortlessly plug your phone into a charger, take a second to appreciate the brilliant, vibrating invisible magic happening right inside that tiny plastic box. Thank you so much for exploring this fascinating topic with me. Keep wondering, keep learning, and I'll catch you on the next explainer.